Welcome to The Explainer. So today, we're going to unpack one of the most fundamental ideas in all of artificial intelligence. How does a machine actually learn from its mistakes? And we're going to do it with a really simple analogy that I promise will make it all click. Okay, let's just dive right in.
So I want you to picture this. You've got a hiker totally lost in a huge mountain range, and they're surrounded by this thick, dense fog. They can't see more than a few feet in front of them, but their goal is simple: get to the lowest point possible, the bottom of the valley. This hiker, this situation, it's the perfect metaphor for a machine learning model trying to learn.
You see, whenever a model makes a guess or a prediction, it's almost never perfectly right, especially at the beginning. And that gap, that difference between its guess and the actual truth, it creates what we can think of as this giant, invisible landscape, a mountain of error. And the model's one and only job? Find the absolute lowest point in that landscape. That's the spot where its predictions are as accurate as they can possibly be.
Okay, but think about our hiker. Before they can even think about taking a step downhill, they need to know their current altitude, right? Just how high up on this mountain of error are they? Well, for a machine learning model, that altitude measurement, its map of wrongness, is a concept that comes from information theory, and it's called cross-entropy.
So to really get cross-entropy, we got to start with this idea of information. Now, in this context, information is really just a measure of surprise. Think about it. If I tell you the sun is going to rise tomorrow, that's not surprising at all, right? It contains basically zero new information. But if I tell you it's going to rain frogs tomorrow, well, that's an extremely low probability event. It's super surprising, and because of that, it is packed with information. Now, building on that, we get to entropy. Entropy just takes that idea of surprise and it averages it out over all the possible things that could happen. So a system where every outcome is equally likely, like flipping a fair coin, has really high entropy. It's unpredictable, so it's more surprising on average. But a system with a super predictable outcome, like rolling a loaded die that always lands on 6, has very low entropy.
And that finally brings us to the star of the show, cross-entropy. This is our altitude meter. What it does is it measures the distance between two different probability distributions. First, the real-world truth, which we'll just call P, and second, the model's prediction, which we'll call Q. A high cross-entropy score means the model's guess is way off. Our hiker is way up on the mountain. A low score means the guess is actually pretty good. We're getting close to that valley floor.
And look, this isn't just some abstract academic idea. It has a huge practical impact. It turns out that using cross-entropy as your map, as your error function, it doesn't just work. It works incredibly well. It actually helps models learn faster and make better, more reliable predictions on new data that it's never even seen before.
Now you might hear people talk about a related idea called KL divergence. They are very, very similar, but there's one key difference. Think of it like this. Cross-entropy tells you the total cost of using your model's wrong map instead of the perfect real one. KL divergence, on the other hand, tells you just the extra cost. For our purposes, when we're trying to get to the bottom of the valley, minimizing one is the same as minimizing the other, so we usually just focus on cross-entropy.
Okay, so our hiker has their map. They know their altitude, their cross-entropy score, but that fog is still just as thick as ever. They know they're high up, but which direction is down? To solve this, they need a strategy, a sort of algorithm for finding the way down, and that algorithm is called gradient descent.
This is really the core problem that gradient descent is built to solve. If you can't see the whole landscape, how do you make the best possible choice from where you are right now to get closer to your goal? You can't just wander around hoping for the best. You need a system.
And the system is honestly just beautiful in its simplicity. At any given point, you can feel the slope of the ground right under your feet. The gradient, mathematically, is the direction of the steepest uphill slope. So if you want to go down as fast as possible, what do? You just take a step in the exact opposite direction. That one idea, moving against the gradient, that is the heart and soul of this whole process. So the whole process can be broken down into this really simple loop. First, the model starts with a totally random guess. It's somewhere on the mountain. Then it calculates the gradient. Which way is up? Third, it takes a little step in the exact opposite direction, which updates its guess. And then it just repeats over and over and over, one step at a time, literally walking its way down that mountain of error.
And I want to be clear, this isn't just a convenient analogy. It's the mathematical foundation of how this whole thing works. By repeatedly calculating that gradient and just moving against it, the model is pretty much guaranteed to find its way toward a minimum point,
a place where the error is lower.
Okay, now there is one more absolutely critical piece to this whole puzzle. Our hiker knows the direction they need to step in, sure. But how big should that step be? A tiny shuffle? A giant leap? This is one of the single most important settings in all of machine learning, and it's called the learning rate.
And this brings up a classic trade-off. If you take these tiny, little cautious steps, you'll be very precise, but man, it might take you forever to get down the mountain. On the other hand, if you take these giant leaps, you'll make progress way faster, but you risk jumping completely over the lowest point and landing on the other side of the valley, maybe even higher up than where you started. So finding that just right learning rate is absolutely key to training a model well.
So we have our map, that's cross entropy, and we have our compass, that's gradient descent. Let's put it all together and watch this entire learning process happen.
It's this elegant, incredibly powerful cycle. Step 1, the model makes a prediction. Step 2, cross entropy calculates the altitude. It figures out how wrong that prediction was. Step 3, gradient descent finds the direction of steepest descent. Step 4, the model uses that learning rate to take a step in that direction, updating its own internal logic. And step 5, it does the whole thing all over again, getting just a little bit smarter with every single loop.
We've been talking about high scores and low scores, but that's all a little bit abstract. When you're actually training a model in the real world, what do these numbers really mean? What should you actually be looking for?
Here's a kind of practical, back-of-the-napkin guide. A score of 0 means your model's predictions are absolutely perfect, which, let's be honest, almost never happens. A score under 0.2 is actually pretty good. Your model is definitely on the right track. But if your score starts creeping up past 0.3, or especially if it goes over 1.0, that's a big red flag that your model is making some seriously poor predictions. Our hiker is still lost way up high on that mountain.
All right, let's pause for a second, look back down the path we've just traveled, and really lock in the key takeaways from all this.
So the big takeaway is this. Cross entropy is the map that tells the model how wrong it is. Gradient descent is the compass that always points it in the direction of being less wrong. The learning rate decides how big of a step it takes on that path. And these three ideas, working together in that continuous loop, they form the fundamental engine that trains countless AI models that are shaping our world right now. And that brings us to one last really interesting thought. This whole strategy is designed to find a valley, what we call a local minimum. But a mountain range is huge and complex. What if there are lots of valleys? How do we know for sure our hiker doesn't get stuck in some small, shallow dip, when the deepest, truest valley, the global minimum, is just over the next ridge? Well, that is a fantastic question for another time.